Thank you for the introduction. My name is Rui Tuo. Today my talk is where the title is Asymptotic Theory for Linear Functionals of Kernel Ridge Regression. So you may wonder, I'm from a Department of Industrial and Systems Engineering. Why am I interested in this kind of theoretical statistics problem? So the first part of my talk, I would like to spend some time to explain why I want to study this type of problem. So talking about my background is industrial statistics. I have a degree. I have a PhD degree in statistics. So I'm one of you. Okay. So my background is industrial statistics, which study statistical problems in like a manufacturing or industrial problems. So here is one typical problem in product or process design in manufacturing, for example. And an abstract sense, I'm not talking about any concrete problem. I'm talking about it's a general type of problem in many scenarios. So the problem is like a regression problem. Okay. So we have X and Y. So input, basically in the language of engineering, input and output. Okay. So here usually input means the configuration of the product or the process. Okay, so that's something we can control. Usually we can control. They are called the control parameters. The control parameter means that if you make a product, you can decide, for example, how large this product is. The dimension is something, at least you have it in mind. You can choose the dimension at your will. Okay, and the response is something related to the quality of the product. And of course, you want to maximize the quality or the product or maximize the quality of the process, right? So the ultimate goal is to find out the optimal setting for those parameters. But from a statistical point of view, we can say that an intermediate goal is to explore the so-called response surface. The response surface means the input-output relationship. If you have a good understanding what the input-output relationship is, then you can have an informed decision, make an informed decision for your product or process design. And the model, statistical model we use here in my talk is a very simple one. It's a non-parametric model. So we start from this model. Okay. So y is equal to f of xi plus epsilon. So f is something you are interested in, which is an underlying function. Usually it's continuous, at least in my talk today. So because response surface usually will assume they are smooth. If you change the input setting a little bit, your quality of product also changes by a little. Okay, and epsilon I is IID error, so mean zero error, and there can be measurement error or some other noise from external sources. Okay, so once we have this model, the goal is, from statistical point of view, is to estimate f. But from the industrial point of view, ultimately we want to make predictions. So what does prediction mean? There are different types of prediction. A simple one is to predict the response value at an untried point, an arbitrary point of interest. Okay. So this gives so what you want is f of x, some new x. Suppose you have some new x, and you want to predict f of x, right? But f is unknown. You want to estimate f from the data. So that's a basic problem. Okay, is that clear? So I think a pretty obvious estimator. Suppose we have a non-parametric estimation, non-parametric estimator of f. We can do this plug-in estimator. Maybe some people may raise the question, why I should use this plug-in estimator, but I just use it because it's so convenient. But some people may ask, what is the minimax type of estimate? I do not know. I really do not know what is minimax one. But I just, in my talk, I always use the plug-in estimator if you want to estimate some function or functional of the unknown function f. Okay. So this plug-in estimator is linear in f hat because it's point evaluation. So that's one type of linear operator for the unknown f. And sometimes we may also wonder, we may also be interested in other types of estimators. And here is a first order derivative, pardon my typo here. I was trying to edit this slide on this computer, but it seems it does not allow me to do so. It says it does not have the right license for the PowerPoint, so pardon this typo. It's a partial derivative of f over x, and then you evaluate that derivative at any point. Okay, so that's also a linear functional or the integral of f. So that reflects overall performance or the average performance, average of the quality across all setting of configuration values. Okay, and those things, of course, can also be estimated by plug-in method. For example, the derivative, I can also replace this f by f hat if I have a estimate, right? So if I can estimate f, then I plug in the first order derivative operator or the integrate operator to it. I can get those estimators. And you may also ask, well, many times my quantity of interest may not be linear in f, right? So what will happen in that case? So those scenarios are also quite common. But one remark I want to make here is that oftentimes those things can also be linearized. So eventually or asymptotically, there is an equivalent linear operator for those ones. So I will introduce two examples. The first one is optimization. So this is directly related to product and process design. So suppose the goal is to find the optimal setting. So you want to optimize this function. Here is a global optimization. You want to find the global optimization of your response surface. Either you want to find the value or the x, the point of x, which maximizes this function. And we can again do plug-in estimation. So very simple. Just replace the underlying unknown f by your estimator. Okay, so you can do that. And the question is here is what are their asymptotic properties? So in terms of those are definitely nonlinear operators. However, you can also tell that those things can asymptotically be linearized. We just do a local Taylor expansion. So for example, this maximum point, if we denote the true value by x0, which is something you do not know. And x hat is a statistic you estimate from the data. And just do a Taylor expansion, this can leave for the students as a homework, very simple one. So if you do a Taylor expansion, you can show that, well, there are some residual terms. If you assume those residual terms are negligible, the leading term will be the ratio between these two quantities. Each one is related to the derivative of f hat and evaluated at this fixed point, x0. So which means that if you have enough understanding of linear operators, then for some, I'm not saying everything, but at least some important linear problems, you also have good understanding. And this one is a simple one, just consider a direct optimization. And in industrial statistics, we may also consider robust optimization, or in OR language, it's called stochastic optimization or something related to that. So here, one scenario in manufacturing is that I actually have two types of x. Sorry, here I use y. Maybe I should not use y because it's kind of abuse of the notation. But just look at this single slide by itself. So I have two types of variables, all on the input side. But one part is something I can control. So I can choose what value this is, which is called control variable. And another one is called noise variable, which are something maybe environmental conditions. So those conditions do exist, and they are varying like a time series or something. You cannot control it. So y has a distribution. X is something you can control. So here, we are facing this robust optimization problem. So this problem can be formulated in different ways. So I just list one of them. So under this formulation, what I do is that I'm taking the expected value, the average over all possible values of y. Okay, and then it becomes a function of x. And next I maximize that function. So the idea here is that I want to maximize the overall, like the average performance of my system. So if that is the case, I can do plugin estimation. So I simply plug in f hat here. So that gives me my plugin estimator. And again, this looks a little more complicated, but I still have this kind of linearization, something analogous to the previous slide. So you can see that both the numerator and the denominator are still linear operators, linear functionals of f hat. And even you can make it more complicated. I'm not using, maybe you don't want to use the expected value, which is just the average case, right? You can also do quantile. So suppose I want my 90% upper quantile or lower quantile to be optimized. If you do some work, they can still be linearized. Okay. So that's one possible problem in industrial statistics, which is related to the linear functionals of non-parametric estimation problems. The second one is something I used to work on. It's called the calibration of computer experiment. So in those problems, well, besides the field experiment, so I also have a different source of data. So basically, I have two different sources of data. One is coming from physical experimentation, and another one is a computer simulation. So computer simulation means that I have a computer code. Okay. The computer code is assumed to be deterministic, which means that the same input always gives you the same output. So there is no random error. So if you have such a computer model, usually it could be like a finite element analysis or neural network or whatever. So those models are deterministic. But usually this model has two issues actually. The first one is that not every, well, they do not have exactly like a matching variables just as the physical data. So in this case, we have one extra set of parameters in this model. So previously I said that there is one input for the physical experiment, which is called X. But now besides X, I have theta, which is an extra input. So which means that the computer model cannot work without specification of both X and theta. So you have to specify both of them. But what theta means, theta is called calibration parameters. Usually they define the physical properties of the model. So the idea here is that the computer model is usually based on some physical theory or physical principle, physical laws. So inside those physical modeling, you will need to use some properties that describing, like the parameters describing the physical properties of the system. For example, permeability or conductivity. So one example is that if you study underground water, like the motion or the distribution of underground water in hydrology, so the permeability of the soil is an important parameter. So if you change that parameter, suppose you can hypothetically change that parameter, the distribution will change, the motion of water will change. But that's something that should have a true value in the real world scenario, but you just do not know it. And the calibration, what we call calibration is just to estimate those parameters from real data. So suppose I have data from both sources. One is from the computer code and another one is from field experimentation. Right. Because the field experimentation, I believe that the data already have some information about that permeability. Then I can use that data to make an adjustment or calibration for the computer model so that I can get a better prediction performance or the fitting accuracy for my computer code. So that's the idea. I think that's the idea. But here comes another issue. So the issue is that actually there is no single value of theta to make these two functions to be equal. So because both of them are functions of the input. But here the thing is that it's just like a model misspecification. So here, computer model is based on a physical modeling. So this physical modeling or mathematical modeling is always based on some assumptions or simplifications, because we do not really know what the true physics is. We have to make some simplifications. Those simplifications can lead the computer output to be deviated from the exact value. So these two are not equal. So if these two are not equal, it brings the problem. The first problem is how do you define what is the true theta? So if no theta can make them perfectly matching, how do I define the true theta? Well, there are different approaches to tackle this problem. One classic method is called Kenny and O'Hagan in their 2001 GISSB paper. So they use a Bayesian approach. So here is their approach. They model, so they just write down the model. YP stands for P stands for physical. So this is the physical response. And if here is, I'm not using the same notation as their paper. I'm trying to use my notation previously. So if basically the first one is a non-parametric regression model. So F is the underlying true response, like we call response surface. And epsilon is the measurement error or the random noise. And the second line links the true response and the computer model. So the relationship is like this. So true response is given by something like this. And theta 0, in their model, they assume there is a true value. So that's a hypothetical true value. And plus some delta called discrepancy between the computer and the physical. Okay, so then how do I estimate theta 0? Then you can see that there is a non-identifiability issue. If you only look at the second line, so second line alone actually already poses a non-identifiability issue because both theta 0 and delta are unknown, right? So basically, if you adjust theta 0, you can always find a corresponding delta that balance this equation. So which means that you can always find different pairs of theta and delta to make this happen. From statistical point of view, this is non-identifiable. So what Kennedy and Hagen did is that they use the Bayesian prior. So hopefully this Bayesian prior can shrink the search space, and then we can do some inference. So they add priors on the Gaussian on the unknown function delta. So this is called the Gaussian process as a prior. I'm not going to the details, but those are just some standard non-parametric Bayesian technique. So once you have the prior, then you can estimate the posterior or either the full posterior density or the posterior mode of theta 0. And in my talk, I call if you do posterior mode, I call it frequentist method. If you do the full Bayesian method, that means you do like MCMC, you do sampling to find the entire distribution. Okay. So the frequentist method, if you just use the posterior mode, some assumptions are here. I'm under some assumptions, I'm not going to go to detail, but I just show you the result. This is the estimate for theta. So theta is the minimizer of this thing. And here is a k. K is a part of the prior, which is the covariance matrix or covariance function of the Gaussian process. Okay. And G is the computer code. Y is the observation. And here one question is that what's the asymptotic property for this one? So this is actually actually pretty important because we know that this problem is non-identifiable. Of course, you can do some Bayesian. You can always say, oh, I have a non-identifiable problem, but I put some prior, then I can always produce a posterior. But from my point of view, you still have to ask this question from a frequentist point of view, right? If I have infinite many of data, where does this go? Right. So from my perspective, it's still important to know that because I really do not believe uncertain like a non-identifiability can always be solved by any priors. I do not think that's always the case. Okay. So that's one thing why this is related to my topic today. I will talk about later. But before that, I talk about some other approaches. As I said, I did see some issues with this method. I do not think this method really like directly address the identifiability issue. So I propose a different method in my paper. So what I did is a pretty straightforward way. If this method, if this model by itself is non-identifiable, then I can enforce a true value. So basically, I define the true value to be something. So then I have a specific goal. Whether this goal is right or wrong is, of course, arguably. But if you accept this is a goal, then the problem is clear cut. You can discuss estimation property, whatever statistical inference or theory for this kind of problem. Okay. So what I do here is that I'm going to use a loss function. So this is the L2 distance between F and G given theta. So you can think in this way. In this model, of course, you can choose theta arbitrarily. If you use the corresponding delta, if you choose that delta accordingly, you can also balance this equation. But different theta will give different delta. So in terms of the size of delta, you have different sizes. And there must be, well, a minimum size of that delta. So that's the intuition behind this work. So we define the true value to be the minimizer of the L2 distance between these two. Then I have the true value. So I can consider whether my statistic is consistent, whether my statistic is having this or not that properties, statistical like a different efficiency or whatever properties. Okay. I do not know. I have to assume it's unique. Yeah, in general, it may not be unique. But thinking about if this is a global minimizer of one function or one surface, I think commonly it should be unique. Of course, you can find counterexamples, but you have to, those are artificial. If the problem is indeed from a real world function, usually that's not the case. That's my assumption. I have to assume it is unique. Okay, and to estimate this one, it's also the same idea. I do plug in estimator. So here, the only thing I do not know is F. G is something I know. I suppose I know G. Okay. So F is unknown. Then I can first use the data to estimate F. So using this non-parametric model. And I plug in my F hat here. And I do this optimization. Suppose I get a unique answer, unique minimizer, global minimizer. Those things are all hypothetical. It depends on whether this can be done numerically, depending on what kind of the size of your problem. But I'm not talking about those practical issues in this talk. Okay, so I call this is my estimator. Okay. So as I said, this definition or this estimator strongly rely on my definition of true value. Actually, in this case, there is no arguably unique true value. So the true value is depending on how do you choose your loss function? So of course, this is not a unique one. Some people may consider different ones. So there are some physical intuition um, or like a scenarios you may consider different ones. So thinking about this is a simple one. I just drew them by hand. So suppose this there is an airplane, and this airplane, suppose we have two airplanes. One of them has a trajectory from this point to this point is like this straight line. One is going up and down, up and down. Okay. So now the question is whether those two motions close when they are not close. Right? So how do you define the distance? So the definition of distance depending on how, like where do you take the observational point? So where do you observe this thing? Right? So suppose you are somewhere under the ground using a radar to scan the trajectory. You may say that these two curves are pretty close. Actually, they can be very close. However, if you are a passenger on that plane, your feeling is completely different. One is pretty smooth. You almost feel nothing. But the other one is just going up and down, a lot of turbulence. So the feeling of the passengers are totally different. So that means, of course, there could be different definition of the different distance, really depending on what kind of context you are in. So what kind of ultimate goal you want to serve, right? So suppose you want to consider the second case in which you are a passenger. You want to really differentiate the red curve from the blue curve. So one possible way, well, of course there are different ways, but one possible way is to introduce the derivative. So those two functions, if you take the L2 distance, they can be very close. However, if you once you take the derivative into consideration, they can be quite different. So this one is done by these two people on the recent JASA paper. They introduced this loss function. So this function, this one is also a norm in a Hilbert space called the Sobolev space H1. So the idea is that I include not only the L2 distance, but also the L2 distance of the derivative. Okay, this is one-dimensional case. If you have multiple dimensions, you take like a partial derivative with respect to each of them. So once you consider this one, it gives you a different result thinking about. Okay. So now if I use this one, I can also define. Suppose this is my true parameter. I can also do plug-in. I just do not write down the plug-in estimate, but you can think I just plug in f hat here. I can also do the same thing. Okay. And lastly, I go back to the KO calibration. As I said, this is the MLE. Actually, it can be proven that this MLE is equivalent, can also be represented in this form. So KO is also minimizing, the ultimate goal of KO is also minimizing some norm, some distance between the computer and the physical. But this distance is different. It's a space called the reproducing kernel Hilbert space. The kernel is the covariance function. I'm going to talk a little bit about what this is later. But this is also Hilbert space. Okay. So that's the thing. So if we summarize all, we have like three scenarios: L2 and the Sobolev one and the KO. We can see that there is a common representation behind all those three estimators. The common representation is that we have a Hilbert space. And we define the true estimator to be the minimizer of these two functions under that Hilbert space norm. And the plug-in estimator is just a plug-in estimator. And under this very general situation, we can write down the linearization. So you can do a little bit of algebraic calculation, you can find out this is the linearization. The 2 times of, it's like a Hessian matrix times the inner product between, this is the error, the non-parametric error, and something related to the computer model by itself. So you can see that, well, at least this part is a linear functional. This Hessian matrix, if it's consistent, it goes to a fixed Hessian function, Hessian matrix. So it doesn't matter. So this one will convert to somewhere, and the second part is a linear function. So you can see that's why I hope I use all those examples to I just want to showcase why I'm interested in the general topic of estimating linear functionals of kernel of the specific method I'm going to introduce. Basically, it's one type of non-parametric regression method. Okay, any questions so far? Okay, so I hope I have introduced the background properly. Oh, okay. So that's the reproducing kernel Hilbert space definition. Basically, it's a Hilbert space. So RKHS is a Hilbert space that such that the linear operator, the point evaluation is a linear operator. So or you can say in this way. So the point evaluation of each function is linear, which can be represented by the inner product because it's a Hilbert space. Okay, and the representer here is called this K is called the reproducing kernel. So that's the definition. And in this talk, of course, you can. So the idea here is that if you choose different K, so K here has to be positive definite function. But if you choose different K, you can get different reproducing kernel Hilbert space. Some space are more important than other one because they have better properties. And in this talk, I only consider a specific one. It's called isotropic Martin. So those are the kernels which are quite commonly used in different statistics and machine learning problems. Okay. The reason we are using this type of kernel, at least in my talk, is that this RKHS can be proven to be equivalent to classic Sobolev space. So basically, those spaces are defined by the L2 of their derivatives, so as I mentioned before. But those derivatives can include high order derivative up to the total order of K. So that's those kind of spaces initially considered in partial differential equations, but in statistics, like approximation theory, people are also using those spaces often. Okay. Here is the non-parametric regression method I'm using in this talk. It's called kernel ridge regression. You can see basically this estimator is defined by minimizing this loss function. The first part is just least squares. The second part is the 2 norm. It's a square of the Hilbert space norm. Here is a smoothing parameter, lambda. Okay. And this one actually has an analytical expression given by the reproducing property of this Hilbert space. I'm not going into the detail, but this is an analytical expression. You can see that it looks like a linear regression, but the X part is replaced by the kernel. So that's why it's called a kernel regression. But also you have this part. It looks like a ridge regression. So that's where the name kernel ridge regression is coming from. And those methods are actually widely used in industrial statistics. So different reasons. The first one is that it does not, there is no restriction on the domain, the shape of the domain. You can see it doesn't matter because we don't choose basis functions. Right? So the shape of the domain or the dimensionality, those things do not matter. So you can always do it. So it's flexible. And also they have natural connections with Gaussian process models, which are also quite useful in industrial statistics. I'm not going to tell the details, but from one slide I showed you before, I said that the Gaussian process MLE is somehow transferred into the reproducing kernel hyperspace norm. So you can see there is some connection between two of them. So those are the reasons why industrial statisticians would like to use those methods. So that's also the reason I want to study the property of this approach. Okay, so what I do here is that the linear functionals of those models. Okay, so there are many examples like point evaluation derivative or the inner product, like L2 inner product. So those are what I talked before. And there are some known asymptotic results in the literature for kernel ridge regression, but mostly on the global performance, like the L2. This is something we know. Okay. The L2, if you choose lambda to be this order, then the L2 prediction error can reach the minimax. This is the minimax rate. So if you're not familiar with those numbers, I give you one specific example. If you do cubic smoothing spline, this is not exactly the RKHS, but you can do something to transfer it to RKHS. So it has a corresponding result. In this case, because it's cubic spline, m is equal to 2, and d is equal to 1, so one dimension. So that's the standard n to the minus 2/5. That's a standard rate of convergence for cubic spline. Maybe many of you are aware of it. And this L2 norm can also be replaced by the empirical L2 norm, which is defined in this way. Okay. So in oftentimes, these two are equivalent in terms of the rate of convergence. So those are existing results in the literature, but they do not cover the linear operators, in our case. So our contribution is that we consider the linear operators, not only the point estimator, but also other functionals. Some of the results are existing in the literature, but I think we are doing some extension, especially for their conditions. I'm not going to go to very technical details about what kind of conditions I have actually relaxed. And I also I do the rate of convergence, and also I give central limit for those things. Okay, and some implications. One thing is uncertain quantification, or we call statistical inference, because now I have central limit theorem. This is possible. And another thing, which is more theoretical, we show that this rate is optimal for the L2 convergence, but it's not optimal for the point estimation. So in the literature, it was conjectured if you can tune your lambda to be good for the global convergence, it is also good for local, but actually it is not true. And of course, this is just a consequence. Okay, so some technical details. Okay, this is a very simple one because it's linear. What I can do is I can separate the bias and the variance. So here the idea is that first, I suppose X is given. There are two scenarios. Either X is deterministic. It's just like in industrial applications. You can choose X. You run the experiment, so X is fixed. No randomness. Or X is random. But if X is random, you can always do, well, from a probability point of view, you can say I'm doing conditionaling on X, right? And I'm under the Gauss Markov assumption that X and epsilon are independent of each other. So that's if you do that, you can regard X as fixed values. This can split the data into the signal and the noise, so that I have the bias and the variance. This is a variance term. So it's a pure random term, which means mean zero random term. And the bias is a deterministic term. And the variance of second one is just given by this one. If I just substitute the variance of the random error denoted by E. So basically E is a vector of the random error. Okay. Now the question is how large is the bias? How large is the variance? If you only do linear algebra, it's quite complicated. It's not going to be working out easily. And we use a different approach. Actually, we introduce a different approach using approximation theory in RKHS. We can handle those things in a much easier way. So here is our idea. So that's what we introduced. We introduced an auxiliary problem. This one is called noiseless kernel ridge regression. So it looks like kernel ridge regression. If you look at the formulation, it's the same. But here the thing is that what I'm doing is I regress this G function. So this G is related to the functional. So this functional is called G. If this is point estimator, this is just reproducing kernel. If it's derivative, it's just derivative of reproducing kernel. Okay. So you may ask the question why I want to do that, because G is something I already know, right? G is something I already know. Why I should do regression on G once again? I say that this is just auxiliary problem. So it has no practical value, but theoretically it has its value. The reason is that the variance can now be represented in this way. And the bias can be represented in this way. So those are all equalities. So much simpler if you compare this one with those matrix formulation, it's much more easy to analyze. So in the end, we only need two quantities. One is the empirical norm, empirical L2 norm, and the norm is a reproducing kernel Hilbert space. So much easier. And those things can be done. And now the problem is purely deterministic because there is no error. You can see G is not subject to random error. So it's completely an approximation theory problem. Okay. So now another thing here is that, well, let's use this one as one example. So if I consider the convergence rate in the reproducing kernel Hilbert space, in the minimax sense, there is no convergence rate. So that's the minimax sense if you consider the worst case scenario of G. But this is helpless. I'm not going to get any good result in that. But the fact here is that if G is actually smoother than the baseline smoothness of this H, this one can converge much faster. So there is convergence. So that's in applied math, it's called the improved rate of convergence, which is quite common in different approximation problems. And also another fact is that because we have, here I use Cauchy-Schwarz inequality. The first one is equality. But Cauchy-Schwarz inequality, we know that it is sharp, which means that the equality, the identity equation can be attained if I'm choosing a specific G. So this can be equation, which means that the worst case scenario, this is called the worst case bias, is also a known value. Okay, so that's the power of those things. And then some approximation theory analysis, of course, we need some assumptions. And as I said before, it really depends on what this, the smoothness of G is, what kind of smoothness G is. So that's the smoothness assumption I have to make. So basically it says that the inner product between G and every V is no more than the right-hand side. So how do I interpret this one? So it's basically a mixed product between the L2 norm and the H norm. So H norm is a stronger norm than L2. So L2 is a weak norm. H is stronger norm. So think about if delta is equal to 0, then this is a trivial equality because this is just Cauchy-Schwarz. If you do Cauchy-Schwarz, because Cg is something related to G, so you can choose Cg to be the Hilbert space norm in the of G. So that becomes a Cauchy-Schwarz, which is trivially true. But if you want delta to be greater than 0, then this is not true for every G. Unless you have some extra smoothness condition in G, you can you can have this one. Okay. And there are some assumptions on the design. Those can be either quasi-uniform or IID. So quasi-uniform basically means that there are some distance between those points. This ratio has to be bounded. So basically, it means one is the maximum, like a radius of a ball which contains no point. The second one is the minimum distance between 2 points. So a specific case is that if you have those grid designs, this is always true. So grid designs are always quasi-uniform. So those are general conditions. And we have some upper bound. So here, I just quickly show you the results because not everyone I believe is interested in those bounds. But the optimal lambda, if you balance this two, will lead you to this value. So it's n-1, independent of the dimension and independent of the smoothness. So if you want to do pointed evaluation, that's always seems to be the optimal order. Okay. And central limit theorem probably it's more useful in statistics because we can use it to construct a confidence interval. But here recall that the statistic or the error can be decomposed into bias and variance. So for the bias, there is no central limit theorem at all because bias is deterministic, no randomness. You cannot expect a central limit theorem for the bias. But central limit theorem can be true for the variance term. Okay, if the so which means that if you assume the bias term is negligible, then you can still use the confidence interval like this. So just show you the quick result. So the central limit theorem relies on Lindeberg's condition. That's every one of you knows. Actually, it's a tricky one because in non-parametric regression, thinking about basically what is Lindeberg condition, it means that each sample, like each random error, contribute a small fraction in the summation, right? So not one of them is dominating the whole thing. But think about non-parametric regression. If you want to, for example, predict at this point, of course you want to use more information in the data, like close to this point. Use less weight on this part. So the weight here is much larger than this one, this part. So how can you still guarantee Lindeberg condition? So there is a kind of conflict between these two kind of ideas. But we can also show interesting thing. So everything will eventually transform into, again, this auxiliary problem. Once you have a good understanding of the auxiliary problem, you can show that Lindeberg condition is always true. So I'm not going to the details. I also have some lower bound result. It relies on some regularity condition, which is kind of opposite direction of this equation for the previous smoothness. This is an equivalent form of the smoothness assumption. Okay. But one thing is that well, those assumptions are quite abstract. But one thing I want to show is that at least for those ones, all of them are true. So those are the results. I have the point evaluation, derivative, and the inner product. I think point evaluation, there are some existing work showing some of the results, like the central limit theorem they have, but not everything is known in the literature. Especially, we have a wide range of lambda. So for every lambda in this wide range, I have those results. And for almost the same range of lambda, I have the central limit theorem. So those are the pretty general results. And under the optimal choice, we can get the optimal order for those rate of convergence. So implication on the nonlinear problem. This is what I said before. So suppose I want to do optimization, and I use the previous linearization. So this is a Hessian matrix. So we have those things. And the one thing here is that the covariance is known. So covariance can be computed in this way. And we have those results. Central limit theorem. and rate of convergence. This is under the optimal choice of lambda. I ran some numerical results. So some test functions, the first one is unit model. This one has many, it goes up and down. So you can see that it depends on the sample size and also how complex the function is, because if the function has many local optimals, maybe you are not picking the right local optimal in the first place. Okay, thank you. Yeah. So I will go quickly. So we consider two types of noise. One is normal noise. One is T distribution with 3 degrees of freedom. Pretty similar results. First, like this easy function is easy. So this is QQ plot. And if we have a quite complicated function, maybe it's way off if the sample size is small. But once you increase the sample size, it will go back to normal distribution. It fit normal distribution pretty well. Okay, we can also have some uniform bounds if you just extend our theory, because you can see inside the absolute sign is something we discussed before. The next step is just to take the supreme of this quantity. You can use one of the supreme inequality, like the maximum inequality, to find those results. This one is the maximum rate of convergence. I think this is new. I did not find this result in the literature for kernel ridge regression, and it matches the minimax rate. So we have to assume the error to be sub-Gaussian. Previously, we do not need the type of error. We only need the second order moment, finite second order moment. And the second one I think is more interesting. So this considers the inner product. The reason is that look at the rate of convergence. This is a kind of central limit theorem rate of convergence. So this generally implies that this thing will eventually converge to a Gaussian process, which is different from the first one. So the first one, we know the rate of convergence, but we do not know the distribution. The second one, once we know the distribution, we can do statistical inference. We can do hypothesis testing. And so I believe the second one has great potential. If you want to test certain properties of your functional estimator, you can consider go this direction. So conclusion, that's what I did in this work, and well, I don't want to read again, but I do want to like foster some collaboration. I do look forward to that. Thank you very much.